Okay, so this is just going to be a quick video on, maybe it's a series, I don't know. We'll see what happens. But this is on the Umbral Calculus, okay? I'm going to begin, with some motivation. And actually an example of the Umbral Calculus that was given by Rota in the book, or I guess it was a collection of articles called Finite Difference Operators. So at one point, among many of the things that Rota studied, he looked at something called Bell numbers. I guess that'd be capitalized. Bell numbers. And what those do, what they describe, okay, are the number of partitions of a set of n elements. So the number of partitions of a set of n elements. Okay? And I would suggest maybe pausing it, maybe getting an idea of what we're talking about here, after we sort of go through one example. They're kind of fun to play with, and they're shockingly hard to find deterministic formulas for. So, to give you an idea, before we start, the only kinds of formulas that we had for this, before Rota kind of got on the scene, to my understanding, is stuff that looked like this, okay? Where you had this sort of recursive formula where you had to have all the previous Bell numbers in order to get the next one. And that's sort of tedious, and it's not super convenient, and everybody loves deterministic formulas, so why the heck not try to find one? Now, in looking at this problem, here's what I mean specifically, okay? Let's take a set of 3 elements, okay? We can all agree this is a set of 3 elements. The problem is, I want to find as many partitions as possible where I'm partitioning this set into different subsets that are non-empty. So I'm just going to start here. I already have a set with 1 block. So here are a few different partitions with 2 blocks. Can you think of any others? No, because there aren't any. That's it. Those are the only partitions with 2 blocks. And then finally, there's 1 partition with 3 blocks. And you can kind of see how you would have a formula that has that choose combinatoric function in it, the combination formula, because what you really are doing is you're breaking this up in a number of blocks, and then you're kind of trying to find ways to fill those individual blocks, okay? And what we have here, when we have a partition like this, okay, this is a partition, okay, and we say that n of pi is 2, and this means the number of blocks, okay? This is just a little piece of terminology, and here we have 1 block, here we have our second block. Again, this is n pi of this partition is 2, n pi of this partition is 2. Over here, we have 3. 1, 2, 3. This is just 1, right? This is a hard problem. So Rota looked at it like this. Let's take this, just a set function, okay? And here I'm gonna use 3 elements because we're working with b sub 3 anyway, and I can kind of do this. But let's generalize just real quickly. Let's say there's n things here and there's u things here, and what I'm setting out to do is find the number of functions between u and s, and you denote it like this. Okay, this is the number of functions between from s to u. Okay, and of course there's u things over here, and each one of these things can go to any of those u things. So you wind up having u times u times u n times. Okay, so it's clearly this, but like many other combinatorial problems, there's more than one way to write it, and if you pick the wrong way, you're going to be in for a lot of symbol crunching. So This is a nice convenient way to write this, but let's just say for a second that I labeled these A, B, and C. Let's just look at what I'm doing, and I kind of have like 1 and maybe 2 and maybe 3, and I send these two to this one, and maybe I send this one to this one over here. Okay, what did I just do? Well, I grouped these two together and sent them both to 1, and then I grouped this one and I sent it to 3. I've just partitioned S. By sending one function over, I partitioned S. I sent A and B to one block, and I sent C to another block. This is exactly this partition right here. And then you might ask, well, if I have a partition, I have pi, a partition, and in this example I have A, B, and C, how many different functions can I have? Okay. How many functions? Well, let's see. I could have sent A and B to 1, 2, or 3, and then all I would have had to have done to make sure this was still a function is just send C to anything except what I sent A and B to. And it still would have been a function even if I had sent it to the same thing, but it wouldn't have preserved this pi I have here. So really what I have is I have u times u minus 1 times blah 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 times u, and then I'm kind of interested in how many blocks I have, right? It depends on how many blocks I have. So I have u minus n of pi plus 1. Right? So in this case, I have 3 times 2. 6 different functions for this pi. Okay? So what I have here now is another way to write the sum. I can just go over all partitions pi, and I can consider the falling factorial, which is what we call that, and this is how we denote it. We have an exponent with parentheses around it. I can have a falling factorial of order n of pi. Now, we're not quite to the realization yet, but we're getting to it really quickly, and maybe we should just get it out of the way. What this is, if I consider all different n, is it's the basis for an algebra, okay? And here's a basis for that algebra. Okay? This algebra is whatever my coefficient field, I'll just choose C, because why the hell not? C of u. Okay? So I have linear combinations that can form any polynomial in C of u. This is a great basis for that. But here's another basis. The falling factorials. Right? It's the same damn thing. And there's a dual basis to this that can send each one of these things to 1. It's called linear functional. So I can define a linear functional that sends all of these things to 1. This is, of course, just a constant. And what I'm really looking is its effect on here, because if I run this L through, what I get is the sum of pi 1 equals L u to the n. Okay, and so let me just let me elaborate a little bit here. What I'm saying is there's a dual space to this that's isomorphic to it, and it's called the space of linear functionals on U. Okay, hang on a second here. All right, and in this space of linear functionals, I can find a linear functional L. Okay, so I can find an L so that L of u to the falling n is 1 for all n. So I just assume that exists, and it does exist. We have theorems that, talk about that. We don't have to get into it. And then I use it up here. All right, and this is really sloppily written, so maybe I'll just recopy this. But the idea is, I'll recopy this with more space. Okay, so what I have here is I have over all the partitions, I have this u to the falling, where this is the number of blocks in my partition, right? Okay, and I have that's equal to u to the n. And if I hit this on this side with L, it's going to squeeze in here. Okay? And I have this. I can't reduce this, but look what this becomes. This becomes the sum over all the partitions, which is the nth Bell number. So this is pretty impressive. I now have a deterministic formula based on this linear functional I know exists. So let's look at this in practice. If we can rewrite, let's say, u cubed in terms of this basis here, and then apply that linear functional, it should just be the sum of the coefficients of what I come up with. Well, I have 1 times u falling 3, plus 3 times u falling 2, plus 1 times u falling 1. And you can check that if you want, but you can trust me also. It does wind up being this, and if I hit L, such that L is defined to take every one of these bases and send them to 1, I get 1 plus 3 plus 1, which is 5. And what did I get for B3? I got 5. So this is sort of interesting, and it's all it is we're changing bases, I don't know, whatever. We're changing bases, basises, in this polynomial ring. And that's the gist of the umbral calculus idea. Now where it gets really powerful is when you start talking about operators, okay? And here's where it comes in with operators. So if you ever play around with finite difference calculus, you'll see that there's actually some pretty sweet shit going on there. Okay, one thing you can do, okay, is you can look at delta for some difference d of f. And of course what I mean when I say that is I'm talking about f of x plus d minus f of x. Well, think about this with me for a second. And that's at f of x. I can also define this. As specifically this series as a Taylor series. And how do I do that? Well, I get all my derivatives, and I start at the point x, and then I increase. What I'm looking for is just d to the k, okay, over k factorial. This is k is 0, all the way to infinity. So I'm starting at f of x, and then I'm increasing by these infinitesimal amounts, not infinitesimal, but by little and little, smaller and smaller pieces until I finally get this form. Okay, so this is just a Taylor series, right? Now the thing is, if we look at operators, one of the ways that they write these things is with uppercase D. And this denotes, maybe you have x in there or something, this denotes the kth derivative with respect to x. Okay? And so if we're writing this specifically in terms of operators, it looks something like this. I have dk, and then lowercase dk. This is actually a constant. This is just an operator. Okay? And I'm applying this as an operator to f of x. Well, this has a series form, a functional form, or a closed form. And it just looks like this. E, D, D, applied to f of x. Now, this is what I specified this to be. Okay? And if I get a little more creative with this, one thing I could say is delta d plus 1, or plus d, but we'll just say delta plus 1, is f of x plus d. Now, again, just considering this in terms of, this would be applied to f of x. Looking at this, and looking at this, I can actually make the claim that this is true. This may seem completely absurd, but just follow me for a second. Suppose, let's say that I wanted the derivative here. Well, if I was solving for d, the capital D here, I would just take the logarithm of both sides. And then I'd divide off by the small d. Now, that might seem absurd again, but in reality, if I break this up into a series, and I take these deltas with higher orders to mean nth differences, or kth differences, or whatever index you're using, this is actually an estimator for the derivative. It works. Here's something even funkier. Suppose that I want the opposite of the difference. Suppose I want the opposite of the difference. What is the opposite of a difference? It's a sum. Well, then I would subtract 1 from both sides. And then I would invert it. And this would be the opposite of a difference, which is a sum. That looks completely stupid. I'm treating these things as if they're elements in a multiplicative ring. Wink, wink, nudge, nudge. But it works. In fact, this is called the Euler-Maclaurin Formula. Summation formula, actually. And it's actually the way that you find, or the way that they used to, I don't know if there's more sophisticated methods now, but it was a primary way to find zeros of the Riemann zeta function. This is a legit formula. You can look it up. Go Wikipedia it. But look what I did. I mean, I did this from these stupid little operator things. And so it was sort of interesting to people that you could treat this derivative as if it was an exponent. And there's a strong reason for that. And it was understood more and more as people got further into this finite difference calculus and this finite difference operator theory that Rhoda sort of brought along. Now the spirit of that now is a little bit different, but we'll run into some examples here in a minute that are kind of interesting, and I'll kind of give you a broad overview. As you can imagine, this whole thing really starts in what Roman called P, which is formal power series. Okay? This is a multiplicative ring. And so I'll get into that here in a minute, maybe in the next video.